So we're going to look at free body diagrams today. Now the derivation of this word's a little funny. I think a free body is an object that you're just analyzing in space, and you're going to put the forces and moments on it to make it into like what I call a force diagram. So I think of these as being like force and moment diagrams. All right, now the technique for doing these is to start off with by figuring out what you want the object to be. After you've done that, what you would do then is to draw a boundary around the object, okay? And then you want to draw in the forces acting on the object. There's two kinds. Contact forces are caused by physical contact. That's why you like to draw the boundary, because it helps you identify where the contact forces are. Body forces are caused by force fields, which for us is gravity. So weight is a body force. We don't really have any other body forces other than weight. In a class like physics, you might have electromagnetic or magnetic fields or things like that, but we won't deal with that. All right, now what you do when you're working through these is you start with the applied forces, what's put on the object. Then you have supports on the object, different types of supports, and they will also exert forces on the objects called reactions. Okay, so I think of the applied forces as being actions. At the supports, you have reactions. Reactions are caused by the motion that the support prevents. So if a support prevents motion in the horizontal plane, it does that by applying forces in the horizontal plane. So when you're looking at how to model these different supports, you look at the motions they prevent and then replace them with forces and perhaps moments. Okay, so reaction forces and moments are required to prevent motion. That's how you look at that. Now, in most cases, the assumption of direction of the force is somewhat arbitrary. As long as you have the line of action right, as long as you have the angle at which the force acts right, you could assume in this case upright or down left, as long as you're both on the same line, and that's the correct line. Having a little trouble with my pen there. There we go. So as long as you do that, you're fine. If you pick incorrectly, or assume incorrectly, I should say, so let's say we assume it's upright, but it's actually down left, when you run the numbers on your calculations, you'll just get a negative answer. So as long as you have the line, the proper orientation of the force picked properly on your free body diagram, you can have it go in either direction. It's not important that you actually predict the direction, because if you get it wrong, you'll just get a negative answer. That's all, and it's easy enough to know what's going on then, okay? Okay, the weight of an object is applied to the center of gravity. So if you have a weight that you're going to consider, you want to put that on the center of gravity of the object. Sometimes we ignore weight if it's small in relation to the forces that are applied. All right, so what I've got in your packet there are just some pictures of different reactions. And let's have a look at these things, or different connections, I should say. Let's see how we model these. Okay, the first one is a cable. Now, a cable force acts in the direction of the cable. So a cable force pulls along the cable itself. So if you know the angle of the cable, you also know the angle of the cable force. That's the idea. Okay. Now, the other thing about cables is all they do is pull. You can't push with a cable. So if you have a cable support on an object, you know both the angle of the reaction and you also know which way it goes because it has to pull. Okay, there's some cables on the on this crane. So if I were to cut a free body diagram of this pulley here, these cable forces would go up. They pull is what they do, and they go up right along the line of the cable. Again, I'm going to have some trouble with my pen here, so you know, that would be right on this line like so, okay? Some more cables there on a, it's a telephone pole, I think. Might be power, I'm not sure. Okay, here's some cables here. These are actually kind of struts or something, but they're holding up the awning. So if you're drawing a free body diagram of the awning, they would pull that way. If by chance you're drawing a free body diagram of the effect of these cables on the building, they'd pull the other way. Okay, so you do have to look and see what it is you're analyzing. Okay. Okay, you can see here the weight of this sine would go down. So these cables here are put in there to pull it back towards the building. Sometimes you see those, something like that on a fence gate. You know, over time a fence gate will tend to sag. Sometimes they'll put cables on it just to get it to pull back up. Okay. Okay, now a linkage is like a cable in that if you know the direction between the two pins on the linkage, the pins being right here and here, you also know the direction of the force. It goes between the two pins. Now linkages are a little different though in that they can push or pull. Okay. Now because links only have forces exerted on the pins, they're called two force members sometimes, and the force runs between the two pins. We'll come back to that when we do trusses. So there's a link right there on the chair, okay? So the forces on this linkage, just depending on what it's doing, and also we might look at what it is we're analyzing. If we're looking at what the linkage does to the chair, it might be doing something like that at the pins. It's hard to tell which way it's going, but something like that. Those forces would run in line between the two pins. Okay, now we get to rollers, rockers, and smooth surfaces, which all act the same. The force of a rocker, roller, and a smooth surface is normal to the surface on which the roller rests, or rocker, or smooth, or this object rests, okay? So if we have no resistance along the line of this surface, the only force then will be perpendicular to the surface, okay? So that'll be a 90-degree angle right there. Okay, there's a smooth surface, so the force of the floor on the end of this broom, if we assume that to be smooth, will be perpendicular to the floor. Okay, there's a roller. There's 4 rollers, okay? So we'll have 4 forces pushing up on the rollers. Again, perpendicular to the surface. Like so. Now, if I put that roller on an incline, the forces will be perpendicular to the incline, like so. So when you've got a roller, rocker, or that object on a smooth surface, you draw the force perpendicular to the surface. So you want to identify what the surface is and draw the forces perpendicular to it. Okay, this is an old drapery rod from long ago. I don't think they make them so much like this anymore. But this connector here is free to rotate about the circular rod right here. Or circular connection, I should say. And these things will slide, you know, this way. That's what they'll do. They're designed to do that. So these are rollers is what they are. Now they're constrained from moving up, down. You know, the force is perpendicular to the surface because they can't move perpendicular to the surface. Okay, so they're rollers. So you could represent the force of the surface on this roller, you know, something like that, or vice versa, you know. Actually, gravity's acting down there, isn't it, in this case? So the force would be up, not down. But regardless, the force will be perpendicular to what you define as the surface. Okay, like so. There's a 3D roller. Same thing. Force is perpendicular to the surface. That just acts in 3 dimensions. Okay, we've got sliding collars, which have this linkage here can rotate, or whatever this object is, I should say, can rotate. So once again, that's going to act a lot like a roller or a rocker. The force will be perpendicular to the surface. The surface in this case is the shaft. Okay. Now we also have pin joints. Now a pin joint holds the object down in place but allows it to rotate. So this object can't move up, down, or left, right. And you could define that either in the classical kind of XY sense, or you could look at a set of axes normal and parallel to that surface. Either way, that object isn't going to move. So there are forces exerted in those two directions now to hold it in place. So the important thing here is the two reactions that you put on a pin joint are perpendicular to one another. You can orient them however you like. Okay? So what we're doing here, we're showing that the forces exerted match the motion that is prevented from occurring. So that pin joint would not allow that linkage to move up, down, or left, right. So the forces are required to do that. Okay. Okay, there's a pin joint right there. Down at the bottom, that takes these struts and holds them down on the bracket. Those struts on their own could rotate if they weren't attached to the roof up here. If they were just, if those struts were just free, they would rotate about those pins. So that's a pin joint. It constrains motion in the X and Y directions. Okay. There's a pin joint on this bridge here. It's an old railroad truss bridge over the Sine River. Okay, there's a pin joint. You see the pin clearly going through there. There's a piston out of an engine. Do you see any pin joints? Okay, right there. I don't know if you've ever looked at a piston, but the piston's free to kind of rotate there about that pin, so that's a pin joint there. Also, where the rod here connects to the crankshaft, that would act like a pin joint too. It would allow rotation, but not motion left or right or up or down. A 3D pin joint is called a ball joint. Okay, so you have a ball with kind of a tight-fitting cup around it that allows rotation in pretty much any direction, but no motion. No motion up, down, left, right, or in the X, Y, or Z directions, I guess you'd say. Okay, you've got a ball joint in your body on your hip. Okay, that's a ball joint there. Here's a ball joint for a trailer hitch. Those are all ball joints. Okay, a universal joint is somewhat like a ball joint. It allows motion, allows rotation about any direction, but won't allow motion any direction. So that's a lot like a ball joint there. Okay, a fixed connection on a collar. That would prevent a moment, so you'd have a couple reaction there plus a force, but we do have the object free to slide in that axis, so we don't have any force going that way. So in this one, we have a force reaction perpendicular to the surface, and we also have that moment reaction that I'm showing, okay? Because this object being solid there in that connection would not be free to rotate. Okay. Okay, a fixed support is called a cantilever support sometimes too, completely locked in. So in 2 dimensions, there are 2 force reactions and a moment reaction is shown there. Okay, so that's a fixed or cantilever support. So there's a fixed support. It's bolted down into that concrete pillar. This light pole here is not going anywhere. It's not going to move left, right. It's not going to move into the page and out of the page, nor will it rotate. It can't do anything. It's all locked in. Okay. There's a fixed support right there. So you see that's actually kind of a cantilever connection right there. You see this roof extending out. Okay, you see it on the inside of the stadium there, that extended out roof. That's a fixed support there. All right, how about drawing a free body diagram of this picture here? This is a sketch. Now you can just draw the free body diagram right on the sketch. Okay, you don't have to make a new sketch of the bracket. You can just put the forces right on there. So we're on page 370, I think. So I'll give that a run. So once you pause the recording and see if you can get a free body diagram of that, then we'll have a look at it. Okay, so let's have a look. there we go. So when you're doing these, don't overthink them. Just focus on each support one at a time. So there's a pin joint. That means that RAX goes to the left, RAY goes up. Now, you could have RAX to the right and RAY down. It doesn't matter. But you do want two forces on that because it's a pin joint. It's a triangle with a rivet at the end. That's how we show pin joints. It prevents motion in 2 dimensions. So we've got forces to show that. Now this roller here is on an inclined surface. All right. So the force will be perpendicular to the surface. This is a 90-degree angle. We've got a 67-degree angle here. So if we take a triangle with 180 degrees minus 90, minus 67, we end up with 23 degrees for the angle of the force. Okay, so the force in these cases always ends up to be 90 minus the ramp angle. The ramp being the surface. We've got the 40-pound weight at G, the 110-pound weight at C. The 40 pounds is the weight of the bracket, which is applied at its center of gravity. Okay. Let's have a look at this one. We're going to pull a box up a ramp. We've got that 600 Newton force we're using. We're going to look at friction here too. Mass of the crate is 70 kilograms. So why don't you pause and give that a try, and we'll have a look. All right, let's have a look. We convert the mass into a weight because we do statics with weights, not masses. That goes at the center of gravity. Then we've got the force of friction acting and a normal force right here. So those are the forces. Now what I chose to do on this one was to dimension it in relation to the ramp. So I've got inclined axes here. I did that because this force is dimensioned on the ramp. The force of friction is parallel to the ramp and the normal force is perpendicular to it. So all I had to do there was calculate the angle for the weight, which would be 17 degrees. Okay. All right, on this one, I've got a 1,700-pound beam. Draw a free body diagram of the beam and a free body diagram of the pulley. So 2 free body diagrams there. So why don't you pause and then give it a run and then have a look. All right, here we go. So let's have a look at the free body diagrams. There we go. So I've circled the beam itself, 1,700 pounds down. Those tensile forces pull up. I did the trigonometry and got the angle. And the pulley has the 1 force up and the 2 forces down. Okay, so these pulls in the cable go different directions depending on what it is you're analyzing. If you analyze the beam, they go up. If you analyze the pulley, they pull down. Okay. All right, let's look at this lever. Exerts a force on the board. The lever is not attached to the fulcrum. The fulcrum is right there. Okay, that's called the fulcrum. Draw a free body diagram of the lever and assume the friction is 0. Okay. Now on this one, we're assuming the friction is 0. We're assuming smooth surfaces here. So we're going to take kind of what I call an idealized look at this. We're not going to make it theoretical. We're going to make it kind of an academic approach. We're going to assume that this bar does not penetrate and bite into the board. Everything's rigid. So we're just going to look at this physical situation using the rules we just covered and drop a free body diagram. Okay, we got a smooth surface here because friction's 0. So the key thing on this is going to be determining what the surfaces are and as far as how you draw the forces. Okay, so why don't you pause and give that a run and check back in. All right, let's have a look. There we go. So we got the 300 Newton pull. Okay, at B, the flat surface there is the bar. That's sitting on the fulcrum, so the force is normal to the bar. At C, the flat surface is the board, so the force pushes on the bar, normal to the board. So we identify what the surfaces are, and then show the force is normal to them. That's the idea on this. Now, we've got that. So we just basically identify the surfaces, show the forces perpendicular to the surfaces. I guess that's really about it. Okay, and keep in mind also that we're showing the forces on the lever. We're not showing what the lever does to the board. We're showing what the board does to the lever. Okay. Okay, let's get a free body diagram of the bar if a child is a quarter of the way across the bar. Notice the connection over here. I've got to zoom in on the connection. Okay, so once you pause and give that a run. Okay, here we go. Have a look. Okay, each of these pin joints gets two forces because those are pin joints. I guess we'd probably also have the weight of the bar going through its center of gravity, which is probably up here somewhere. It's a G there. We have the weight of the child, quarter of the way across, and then we have both of these forces at each pin, RAY, RAX, RBY, RBX. Now I think that RAX and RBX are going to be 0, but I'll show them on the diagram because I've got a pin joint there. Okay. Now my equations could show that RAX and RBX are 0, but I'll show them because they have the potential to occur because pin joints can generate an RAX and an RBX as well as the RAY and RBY. Okay, let's draw a free body diagram of this top armature. Okay, so there we go. So have a look at that. Pay some attention to the connections there. Resolution isn't the best there, but it looks like we've got a cable over here. Think about how that would be connected there and model these things. So what are they? And once you know, assume what they are, put the forces on there to correspond to your assumptions. Okay, so once you pause and give that a run, then we'll have a look. All right, there we go. So what I did there, I took the head of this thing off. Okay, so I kind of analyzed that separately. So I got its own center of gravity, and I've got the weight of it there. And I have the weight of this beam here at its center of gravity. That's a cable, so I'm assuming it's pulling. I'm assuming this is a pin joint here, so I got RCY, RCX, and then this linkage I'm assuming is pulling down right now. So there's my free body diagram. Okay. Okay, one last one there. We've got this stop sign beam here. Notice the connection. I've got to zoom on the connection. Notice the taper of the beam too. It's tapered as it extends out. So see if you can draw that up and then pause the recording first, see if you can draw it up and then have a look at what we got. Okay, so let's have a look. There we go. So what we got here with these bolts was that's a cantilever support. So I got REX, REY, and a reactive moment at E. I've got the beam extending out, the center of gravity of the beam. A little hard to read there, but that's a G. I've got that further to the right because the beam is tapered. And then each of these signs exerts weights. Okay, so that's what I've got on that one. All right, so for homework here, do some free body diagrams. I think they're 251 through 255, and they're on page 12A and 12B. So what I would like you to do on those is just pull pages 12A and 12B out of your packet and turn those sketches into free body diagrams by adding forces to them. So you don't need to draw up your own homework statements or anything. All you got to do is pull out pages 12A and 12B and put the forces on the sketches for 251 through 255. Okay? And get your name on there, and that should be fine. So we're looking at 251 through 255. And we'll make these due on Monday next week. And just do your work on 12A and 12B. And I'm pretty sure we're talking about the 29th, I think, on Monday. Pretty sure. So there you go. So we'll call it good.